Well, yes, my name is Stefan Ivanell. I'm a professor and head of the wind energy section, Uppsala University, and also director for Stand Up for Wind, which is a national wind center in Sweden gathering wind activities at 4 universities. And today I will talk about multiscale modeling, the topic of the session as well. And the work I will present today is also in collaboration with my colleagues, Hugo, Gonzalo, Johan, Henrik, and Huidong, where Hugo been working mainly with LES in the forests, I will show. Gonzalo, some RANS results we will see, and Johan experiments, and Henrik some LBM methods, and Huidong some WRF simulations. You will see later on. So then, when I was invited to give this talk, thanks by the way, Jake, for that. I was asked if I could give the modeling news on multiscale from Uppsala, and I started to think, what should I then present, since most of the things we are doing are more multiscale, more or less. So we've been working with farm modeling for many years, of course, very multiscale problem depending on how you define it. And here we've been mainly focused on LES. We have some more novel methods, still LES, but I will say a few more words about that. And then we've been working on farm wakes and the farm-farm interaction and also blockage. And of course, in here, inside the wind farms, we have the smallest scales generated within the farm, but also interaction with the largest scales, the Earth rotation scales. So it's really a multi-scale challenge here to model this. And here we've been working with WRF and LES. And then last years, we also spent a lot of effort to develop forest models to represent the flow inside Swedish forest. To a great extent. So today I will touch upon this. I will very briefly say something about farms, just mentioning some new novel methods that might increase the possibilities to run multi-scale models in more efficient in time with farms. And then I will say something also short about the farm wakes. Here we know that there's a need to develop engineering models and they need to be calibrated, validated. I will say something about how I can do that. And then I call here the ultimate challenge. I don't know if that is the ultimate, but at least I put it here in this presentation as this and see how can we then model this. And this is where I will spend the most time of today's presentation on the forest models. So I will very quickly say something about farms, a little bit more of farm wakes, and then concentrate on forest modeling, and then some summary and conclusions. So first, farm models. We've been working on that with standard LES, let's say, for many years. And recently, we've been working with lattice-Boltzmann methodologies that has been used for other applications than wind for some time. But here we have, we have a publication coming out very soon on a new wall model, which makes it possible to run atmospheric boundary layers. And that is, I think, a big step forward to be able to run the cases we do. And that opens up possibilities to run wind farms on GPUs on a desktop machine more or less in real time. So it's a great increase in computational need there, or decrease in computational need. So that is then also opening up possibilities for machine learning, etc., for farm optimization. So that I think is coming, and of course that could then also be coupled with more micro mesoscale coupling, but I will touch upon that a little bit more later on. So that's what I want to say about farm modeling, and then I will move on to farm wakes. So this is some preliminary results. I will not go into all details here, but this is the result from a farm in the Baltic Sea using WRF. And it's no surprise that the wake length and the wake deflection depend a lot on stability. But this is quite heavy simulations to do this, and we need engineering models to be able to plan for a lot of offshore wind farms for the future. And we have a collaboration with Durham University where we do develop this type of engineering models, but here we also need input from high fidelity models. So here's an example with LES, instantaneous results and time averaged. But these are quite heavy, and we then need to validate and calibrate these engineering models. And therefore, we looked into, can RANs do the job for this good enough? So we can run these cases quite efficiently in CFD measures and see how well can we do this. So this is just some examples of results. This is a bit of the talk, so hopefully we can present this later on more in detail. But as you shows a comparison with LES in this case, no measurements, but with LES and RANs. And we can see that if we set up the RANs cases in the right way, we can capture the velocity deficit and the turbulent kinetic energy inside the wind farm and also in the farm wake fairly well. So that speeds up our abilities to create validation data and the calibration data for engineering models. So that is what I'm going to say about farm wakes. But it opens up for, more multi-scale possibilities also when it comes to farm interaction. And then I will go to my main topic on forest models. And this is what I call the ultimate challenge. Why? Well, we have the turbines here and interacting with atmospheric boundary layer. We have lakes and complex terrain. We have the time-varying atmospheric conditions, so diurnal cycles. So how do we model this? This is quite challenging. And if we think about how can we model the turbines, well, we can use actuator line to actuator disks that we've done for many years. So that we know pretty well how to do. I will not today show any results on turbine interacting with the forest boundary layer, but of course we can combine these models with actuator line and actuator disks as well and represent the turbines. Next question is then, how do we represent the forest flows itself? And here we've been spending quite a lot of effort, started in the NEVA project, and then we continue that work. So this is an example from a test case benchmark in Sweden called Rynäsnäs. We've had 2 turbines and a clearing. And you can see here the airborne laser. So we have laser scans over all forested areas in Sweden, which is fortunate. And then we can map the forest very detailed. And then we can calculate leaf area index, and then we can put that into our simulations to really have a well-represented forest. And then we run a number of tests. How can we do this, and what do we need to do to really map the flow in the best way? And this is an example where we show if we would represent the forest in a box. Let's see if I can point here, maybe. No, I cannot do that. But you see on the upper picture there that we represent the forest well with these laser scans in this box, which is, well, not that small, it's a number of kilometers. But then we compare if we represent this in an even larger area, what's the impact of that? How large area do we need to represent with this detailed representation of forest? And then the figure here you can see, flat terrain here means that we don't have the leaf area index representation in the model, but we have the roughness, and then we compare with the smaller area and the larger area. And then you can see the TKE normalized with U star squared, and you can see that when we have this full domain, we can represent this quite well. Then if we look into another case, similar, but from 3 different directions, we can then see the footprint will be quite different depending on what angle we are considering. And the figure here on the right-hand side shows the same as before. It's a bit messy here, but what you can see is the measurements from 3 different directions. And then you can see that if we represent this forest many kilometers away, we can get very good agreement with the measurements. So it shows that with realistic forest topography for many kilometers upstream, the full profile can be reproduced very well. It's quite expensive numerically to do this, but we can represent this very well today. But that is, so far I only been talking about neutral cases. So then we approach the, ultimate challenge, or at least more challenges, and that is when we look into the diurnal cycle in this. How can we do this in a good way? So this is an example, just as a motivation. We have, there's some errors on the slides here, but what you can see here is results from a benchmark called Hornamossen that we did. I will not go into all details on that, but what it shows is that if we look at all data from this benchmark and see and separate it for stability, we can see that all these data do not average to a neutral case, quite far from it. And we know this, of course, but this motivates why we really need to look into the diurnal cycle. Typically, otherwise, in LES, we can assume neutral. I think that is a good guess, and that's what we've been doing for many years, but we really need to look into the stability here. So, therefore, we have developed our model chain, and we use for this work, we use OpenFOAM, an in-house version of it that we have developed. And here we then need to drive the flow with mesoscale simulations for realistic atmospheric conditions and transient features. And then the big question is, of course, how do we represent the forest in this case, and how do we drive the flow here? So this is an example of squared forest, is what you see here with velocities and temperature in these pictures here. So we just have a square forest. And then inside the forest, we prescribe the net radiation. And outside the forest, we prescribe the temperature variation. So this is the approach we used to get the diurnal cycle into the forest, let's say. So then, if we look into how will this look on a vertical cut, to see what implications will this have inside the forest. So what you see here is above the forest, we then have the radiation, and then inside the forest we have the leaf area index that, of course, will vary. So the radiation will not penetrate down to the ground, and therefore you can see in the lower picture there the variations of heat fluxes with height, but also with time. You can see the time here, it goes from 8 hours to 48 hours. So the heat flux will vary with height and time for all of the prescribed conditions there. Now my pointer doesn't work. Well, let's see. Now it works. So then we run simulations on data from this Hundertwasser benchmark. And this is just an example of a few days here. You can see in the radiation plot on the lower right that this is, moderate cloudy day for this case. But of course, we pick a day where we have as constant variation, wind direction and wind speed, and, not as cloudy for validation to begin with. And then we look into how we can then drive this flow. So we use WRF. In this case, it comes from Roberto at CENER that has provided us with the WRF data for the Hundertwasser benchmark that we developed. And here we can extract the the horizontal velocity vector and calculate the pressure gradient. And then, of course, we have the Coriolis included in this. And then from the WRF, we can extract the temperature and also the global radiation. So then we can put this into our forest model, and hopefully this will be a good representation of the diurnal cycle inside the forest. But then the big problem or the big question is, how do we best drive this flow? We can use a vertical uniform and fixed in time pressure gradient, and that's what we typically always do. But we can also use a vertical uniform, but time varying that, depending on then the input we get from WRF. Or we can vary both in time and height, and then we approach the tendencies method that Javier Sanz and others has been developed. We are looking into the tendencies methods. I will not show any result of that today, but I will show results mainly on the second part here, the second point, and discuss a bit around that. The reason why we haven't spend more time on tendencies yet is that so far we have not beaten the second way of doing this, let's say. But that depends on different aspects that I don't think we have time to go into today. But then if we have these methods, so what you see here is on the upper left, constant uniform and constant in time. So you can see then how the LES follows the WRF simulations. And then on the upper right, you see when we use this vertical uniform but transient. And I think this relates to Hugo's question to Björke before, that we get these oscillations because we have some mismatch in the balance between the WRF and LES here. So we have some equilibrium issues there. But then on the lower right-hand side, you can see, sorry, maybe it's hard to read here. What you see here is the velocity vector at 3 different heights. We have it at the 93, 205, and 540 meters. So on the lower right-hand side, you then see that we still have the vertical uniform and transient, but here we force the pressure gradient at 92 meter height, as we so-called nudging. So then you see that the LES follows the WRF much better here. So it looks like it works out very, very fine.
1 or 2 minutes.
Yes, and then this is what we do. We have this LES set up with periodic boundary conditions, and we start this simulation at 11, and then we let it speed up for 6 hours. So 5 a.m. We start the diurnal cycle, And then we have this case, which is a test mesh. So we have 6 million points here, but as it is a test mesh, this costs about 70,000 CPU hours. So with LES measure, it's not extremely expensive, but of course it's still a test case. You see we have a resolution of 50 meters, and you can also see the met mast in the center of this domain here. So what you see on the lower part here is the vertical uniform and constant time method. In the middle, you have it transient, and on the right-hand side, you had it transient with nudging. So hopefully I press this, and all these animations start at the same time. If everything goes, yes, it works. And what you can see here then is how the LES develops according to the WRF. And you see on the left-hand side that there's some offset. You see in the middle part that you have these oscillations occurring, and then on the right-hand side you see this result with the nudging. And the one on the right-hand side we think is very good. So we can really prescribe the flow with WRF, and the LES follows that. And I will not show any results here comparing with measurements, because this is a benchmark that is still a blind test. We will not do that yet, and this is still a test mesh here. But just saying also that this benchmark that we have, Hundamossen, unfortunately the web page with Windvane blog doesn't work right now, but if you Google or search for Hundamossen YouTube, you can also find a video of this benchmark if you are interested to follow more news from it. And it's really focused now on the model chain development on this. So then I will go to conclusions. Well, first part I just mentioned very briefly was the lattice Boltzmann in farms. And here, this LES approach looks very promising. Now we have an atmospheric boundary layer, and we can use that then for optimization, and possibly also drive that one with WRF, as we showed with the other open foam here. But that's far ahead, I would say. And then the second part was that RAND can provide important calibration data for farm wakes, which this was new for me. And then the last part here, the LES approach to model typical Swedish forest has been showing excellent agreement in neutral conditions, and that has been published before, and we've seen that. But now we then have been implementing this new diurnal cycle in the forest and tested different forcing methods, and it looks very promising, and it reproduces the trends and temperature variation very well. But this was still a test case. There will be a full case and then validation against this extensive measurement campaign that we had in Hundamossen. And with that, there's a lot to learn about parameterization of boundary condition and forcing strategies, and useful for setting and testing RAND's linearized models of stability transition over forests. So I think I made it in time. Yes. Yeah. Thank you.
Yes, thanks, Stefan. Also, because the time means that we have also time to answer the questions that were coming in. So Javier Monduet has said, asked Stefan, thank you for your presentation. What is the difference between the RANDs limited and no limited setup?
Well, it's a length scale limiter in the RANDs. So typically in RANDs you can set that, but when looking into this farm wakes, you really need to not have that setting in the RAND setup.
Mm-hmm. Thank you. And then Richard Stevens asks, very interesting talk, Stefan. On the first part of your presentation, how do you define the wind farm cluster wake length?
The first part of...
Yeah, you showed some slides with axes with wake length.
Yeah, you mean in this yes, in this WRF results, yes. In that case, I think we define it as 90%, if I recall correct. There's a publication coming soon, hopefully, where it's fairly clear. But if I remember correctly, we did a lot of spent a lot of time on methodology, how to look into the farm wake turning and the turning just behind the wind farms. So it's really that paper will be a lot of methodology how to categorize that. So that is a big part of the study. But what I show here, I think, is 90% of the velocity, if I recall correct.
Thank you. And do we have any questions from the audience, the in-person physical audience here? I have a question for you.
Yeah.
Yeah. So also kind of thinking about, we've been talking about offshore and onshore, and there's still a huge need to expand for the land-based wind.
Yeah.
And this is, of course, very relevant for that. Where do you see its biggest advantage? Is it in the sort of resource assessment part, or is it in more like the site suitability part? You've shown graphs with, for example, TKE, but you've also shown graphs with wind speed, and so I'm interested which part.
I guess both, but I think going to this level is really in the site assessment, because we know manufacturers going into the Swedish forest or Finnish forest or whatever, and they run into surprises. The turbines doesn't behave as they expect. The control system is not developed for this. So it's really understanding of the details on this side. And what we see is that you really need to map the forest very far away. The footprint is much longer than we expected when we started to study this as well. So it's really important to have that in consideration. Of course, that is not possible to do with typical industrial codes, because these are quite expensive simulations. But what we learned then, that has a huge impact on the performance on the turbines.
And maybe one other question is related to the GPUs. What does that open up in the future?
Well, today my PhD student, Henrik Asmuth, that soon will defend his PhD. He can run farm real-time on his desktop GPU machine in the office, more or less, while his colleagues run on supercomputers with the standard LES. And then we're looking into machine learning techniques, how to optimize wind farms. Of course, that opened up new possibilities. There's still quite new approach to it, and this wall model is also coming out in the publication soon. So it is rather recent work where we can really represent the boundary layer, and then of course how to generate all other things we do in standard LES methods is still to come. But it shows very promising results, especially considering farm optimization and farm flow control in that way, I would say.
Thank you. So let's thank Stefan once again. Thank you.
Thank you.